2 seconds. I just think about it. Straight to the point, Dev. So it's interesting. I presume from that kind of a comment, you've got some good experience of navigating around CAD systems. It's funny, you know, when it comes to component design, and if you want to do assemblies and knock together a good assembly quickly, I actually find that Dassault with CATIA and in SolidWorks, they do some cracking assemblies. However, if you want to do designs where you're going to do some topological optimization, it's going to have some almost organic approach to it, so it's not going to have very many straight lines. So surfaces, if you want to handle 3D prints, anything like that, Inventor is amazing. It is absolutely amazing. However, I do find some of the tools in SolidWorks just give it that edge for you to be able to speed things up.
Oh, the constraints was a pain in the ass.
Oh, you mean on Inventor? It's funny, you know.
Yeah.
Now I got into using Inventor, some of the constraints that are on it, yes, they were an interesting one to get into. But once you get used to the constraint through to joints, I found it really good, really good.
It's a very good piece of kit. It's just I prefer SolidWorks.
Yeah. And the truth of it is they do sit on the they're practically the same system, aren't they?
Yeah, basically.
I mean, I do surfacing on Advanced CAD, and this year we've been able to really run the two to the ground. And some things SolidWorks does better, and some things Inventor does better, and we've got proof of it.
If you want to get yourself into a good practice, I would go with Inventor first, because the way it is with the rules, it puts you in good stead.
Well, yeah, I mean, on the Advanced CAD that we do, on the second semester, we actually go to the root, so we start to program it to build toolboxes. And I find SolidWorks is better for being able to issue commands to actually automate the process. But Inventor's very stubborn, let's say. But as far as research goes, I'm able to use this as a tool just because they don't. Autodesk will give this away if you're not making any money on it, so they let you use it for free. However, Dassault say if you use anything outside of teaching, will basically screw you. So yeah, it becomes quite tricky.
You got like 3 years if you were a student.
I know. Well, I control the university license, and even that's been a problem. Right, yeah. The other important thing about this design is, if you look at where I've actually done it, I've come from the datum and actually done almost, if you will, a mid-extrusion. But I'm sweeping. I mean, I'm revolving around that particular point. So, setting up belts and pulleys. What I'll quickly do is I'll just put the pulley on Blackboard, just so you can actually see what it is. Now, I've already converted it to a step file, and obviously the step file is vital as far as this goes. Funnily enough, I did have some problems with it last week, but that's just something else completely. Let me just stick this up. So yeah, I've put it into a step file, and the most important thing about it is its radius is 20 millimeters. So you'll see why once we start to set this up. I have set up a dummy file, a dummy pulley this morning, just because I wanted to make sure I wasn't going to get myself into an awkward spot. Because this system, if you've not done everything with it, as you're finding, if you've not covered everything, it'll go like that. No, not today. So I wanted to make sure that everything was sorted on it, because I don't want to spend a long time with this. I think I've just seen a question come through. Just 2 seconds. Let me just upload this pulley, and then I'll take a look at that. So, just uploading the pulley. Right, so let me just have a look at if any question come through. Oh, right, yes. that was something else completely. Right, so I've just uploaded the pulley. Yeah, I've just uploaded the pulley, and if you do want to follow, you're more than welcome to follow. Again, I'm not going to spend a long time messing with it, but I did want to take you through the process, and I've been recently getting used to using this because of we're actually doing a project which is using this type of system. Now I'm going to set up the most bog standard, boring version of this that you've ever seen, which is just basically pulley, brake, pull. That's it. But there's loads of good things that you can pull from it. So I'm going to go simulate model and create a blank model. I was recently, now this is how sad I am, I say recently, the weekend, I was reading about the new versions of Multibody, and there is now frictional blocks been introduced, so you can actually apply direct coefficient of friction straight to your system, and this can even be coefficient of friction between polymer and ceramic, which blew my mind a bit, because that is a big statement, massive statement. Right, so as normal, you've got to set up your world. I'm going to quickly set up my world. It sounds weird saying that. I'll quickly set up my world. I'm bringing mechanism configuration. Going to go my world. My world frame. These are my 3 building blocks of every single good system that I need. And let me just pull that into there, pull it into there, and get this nice and tidily set up. Then what I'm going to do is, now this is a pulley, so if I just quickly pull that back up, and you imagine that this is sitting in space, it's got a, maybe I should have put a hole in it just for completion, it's got a hole in it, and it's got a belt which wraps around it, and it's going to pull up a mass, simple as that, simple pulley. What I know from that is it's kind of like the torque that we did, if you remember. So on the torque it was a revolute joint, and that's how I'm going to operate with it. So I'm pretty much concentrated on whatever the motor will be that I'm going to apply to it. At the moment, what I'm actually going to do is just set up a free flowing system until I get it all set up, until it tells me there's no problems, until it tells me there's no errors. Because any of you who've been setting this up at the moment, you'll know that it comes up and says no error, doesn't work. Brilliant. So I'm going to go over to my body and I'm going to drag and drop a file solid. Double click in, and as normal what I'll do is I'll go to my pulley and I'm just going to load that in. This is just on the pulley system itself, so I'll just set 7600. That's just me making the value up. I think that's Ali. I think I could be wrong. I need to check. So tab that in, and then as normal, personally when I set up any simulation, never take huge steps, don't rush. So if I just click run, all it'll give me is the wheel, nothing more. So I know that's there. Now the reason I rushed when I went through the model is I was cocky. I knew one thing in particular. I knew that if we just jump back in, I'll show you. I knew that if I put on my pulley, now the way I drew it, and the way I particularly drew it, is I drew it from the centre. So I drew it knowing that I was going to put this into here, and I was doing it because I wanted to simplify the need for messing around with frames and things. So I put that in there just to give us that angle, that edge, if you will. Alright, yeah, just double checking I turned on the microphone, because that's a common one for me. So, right, and I've got everything in there, so I don't need to mess around with pulleys. Everything is in order, everything is sorted. Right. Who's trying to get on? So, right, so what I'll do now is, we've now got it in. Now, what I want to do is I want to set up a cable which feeds all the way around it. So if I go to belts and cables, again, this is an extra. This is not something you have to put into your assignment. So please don't think that I'm showing you this to do that. I'm doing this just because for those of you who are finding this fascinating, who are seeing the potential where this can go, you may want to see more and more, because like myself, you just get hungry to see more and more examples of how this can be used and what you can do with it. Again, if there is any burning questions about the assignment though, please do stop me, because I am more than happy to divert to them problems or anything like that. Right, so in the belts and cables, now these look really soft and innocent. They're a pain. They're a huge pain. So first things first, it says, give me a belt cable spool. Now this is what I like to think of as a translation block. What it actually says is, if this is where your cable's going to sit, where is it connected? So I say, right, it's going to be connected here. And what that is now is that comes from the original position of where your central axis sits. So if you think of where the frame is in the middle of the actual dial of the pulley. And what we're then going to do is it's going to say, well, what's the radius of that that pulley that you're using? Hence why we needed to know what the radius was. So if I double click in, you come in and let's just bring that down a bit. You can sense the amount of feed it's actually got. You can sense the feet and angles in which way you're going. It is pretty mint what it can do. It's dead impressive, to be honest. So it asks for a pitch radius. So basically, what is that radius that we're going to sit on? So I'm going to drop this to millimeters for one. And within my pitch radius, I'm now going to change that to 20 and apply. This isn't quite fixed yet, but let's take a look at it. So if I click run, I've got so many windows open, I get myself lost here. You look there and you go, well, that's actually done nothing. Brilliant. So then you kind of go, right, okay. Now the next thing it actually asks for is, so I'll click OK on that. Next thing it's now actually asking for is it's actually asking about the cable itself. It wants to know what the cable does. So it wants to know about the belt cable properties. Now within the belt cable properties, it is very dead straightforward. So if I drag this in, this is the type of belt cable that we're going to be using. Is it closed? Is it like a chain for a bike? Is it a continuously feeding thing? So is it restricted or unrestricted, or what is the actual thing that it can do? So I'll tab that in. This won't fix it just yet, but if I tab that in, double click in, see there we've got restriction, and we've got we can have visual type, so I can turn it off completely, or I can have a visualization. Now I always use yellow because it just reminds me of Kevlar feeds. Because I use a lot of Kevlar feeds in any type of drawstrings that I've ever used. Hence why I always use yellow. So with it being unrestricted, it means I can hold it steady, or I can let it go. I can let a mass drop into infinity, or I can drag it back, or I can have it monitor as through planar, where what it will do is I can actually hold its position, or I can actually bring it round to another point. So in other words, I can belt it off completely. So if I click on unrestricted, and that's how I'll keep it. So if I run again, just to see, and don't get me wrong, this is still going to happen just because there's many things that we've not exactly fixed yet. Now the frustrating thing is if I come into here and I do an update, you kind of go, well, where the hell is it? Where's it gone? What's going on? Still confused. So the only reason I'm going through it this way is just because you do come away and go, what the hell am I doing wrong? So the next thing it wants to know is the way that your spool is interfaced. It now knows how the cable's going to behave. Now it wants to know what is the relation going to be from this point to the next position. I could say feed to a pulley, so I can put multiple pulleys on. So if I double click into, in fact I'm not going to use this, but let me just double click in. If I double click into this, you can see here we've got lower bounds, upper bounds, we've got the pitch radius from the original pulley, and what it will do is it will feed cables further. Now this is a way of extending what we're going to do here, but if I delete that Because what I'm going to do is just create that basic motorized mass lifter, if you will, or whatever you want to call it. So I'm going to drag and drop a belt cable end, and all I'm actually saying here is this spool is attached to the dial and the belt cable actually sits further down. That's all I'm saying, is that I'm not actually attached to anything else but a mass. So I tab that into there, and we're now at a nice steady state. It's in a nice position. However, let me just bring back, let me see if it's going to give us any visualization. I don't think this will give us any visualization yet, but I thought I'd just get, oh yes it will, right. So now if you look, it now knows that it's going to be connected. But you look and you go, well, how the hell does it know where the mass is going to be? It doesn't. That's the next bit of this. So what I've got to do is I've got to tell the system how to feed that mass into position. Now, the one thing that I haven't pointed out quite heavily is this type of simulation is impossible in SolidWorks. In I think Nastran can now do it, but SolidWorks totally impossible. Inventor, all your motion built-in softwares, strings, cables and chains are impossible. It is a nightmare being able to do anything like that. You can put sketches on there, but they will never be a representation like this will be. So this is where this will shine in its own right, because it is immense what it can do. Right, so what I want to do is I want to now stretch that cable down and put it into a present state. But first things first, let's get a load into position. So I'm going to go down to my bodies, drag and drop a Brick Solid. Such an original name. I'll just call that load. So bring that into load, and what I'll do is just tab that straight over the top. Again, it's a really great tool is this. So with the brick load straight over the top, what I can do here is I can choose sizes, I can choose whatever I need with it. This is like the crappiest way of modelling that you've ever seen. But what I'll do is go millimeters, and I'm just going to make it 10 by 10 by 10, just to mass really. So I've got 10 by 10 by 10, then click F5 and then apply. And for my loading, I can choose whatever materials that I want here. So I'll go by mass. I'll go density. Let's go density. Let's go 8500. Apply, and then OK. And that's it. So that's my loading in position. So let's just take a look again. Now this is where you'll start to get really annoyed. I got really annoyed when I first learning this. You can put it on. You go, what the hell is that? The reason I put this load on now is it really spells something out massively for you. Look at where the load is sitting. The load is sitting in the middle of it, because what the actual frame has done from the load is it's connected with the center of the original model. It's just clicking back to that position. It's going back to where the world position is. So what this actually means is we've got to just push it out into a position. That's all. Bit of a nightmare, bit of a pain in the arse, I agree. But it's what we need to do. So what I'll do is pop this back out. You can have some fun with this though. You really can have some fun with this. So I'll show you what I mean. What we're going to do is we're going to apply some rigid transforms. So I'm going to bring in a frame and go rigid transform. Now what I do is I go from this position, and what I'm attempting to do is almost stretch out a new world position. It's just because I can give two reference points, one being where the pulley is, and the other being where the mass is. And then all I need to do is then run it from there. So it's a sneaky way of doing it, really. Well, at least I think it is. So I'm going to drag and drop a connector onto here. Again, this is me pulling the cable down, saying where that cable's going to be. Then the Lord interfaces from this new world position that I'm defining. I know this is really confusing, and this is the bit where I wanted to not spend long with it, and this is why I've just chosen a single pulley. Because getting used to playing around with them values where they sit. Now the Cartesian relationship, it sounds really sophisticated. Basically, where's your X, Y, Z? So I'm going to say along my X, I'm going to make it 50 millimeters. This is just me, 50 millimeters. Could make it 60, could make it more, could make it less, whatever you want. And what I'll do is from my Y position, which is going to be at the side of the actual wheel, I'll go 20 millimeters, which is the pitch rad. So first things first, this won't fix it just yet. But if I come back in, I wonder if it's going to give me something nice for me to look at. Does it give me something nice to look at? No, not yet. We still need to move a lot more. Because there is one last thing that we've not really covered just yet. Then, what I really need to do is I need to say how that mass is going to move. Now in this case, I'm going to presume that this mass is going to move prismatic. It's going to move up and down. Simple as that. It's many things that we've done already. So if I go joints, prismatic joint, I'm going to drag and drop that in. What I'm going to do is I'm going to flip this round. I want this to feed from a new world. So what might be a good idea is to start establishing where that world's going to be. So I'm going to flip that round. And I'm going to pull into here. Oh, good God, sorry about that. And I'm going to go Friends and Transforms, and I'm going to bring in a world frame. I know it's a bit dodgy at the minute, bringing in a second world frame, but it is an ultimate reference point, so I'm making 2 points of reference from the start, which is almost a bit naughty really, but it is what I can do. Now, the important thing I need to keep in mind is Z, my Z component, this upwards, is always the way that the axis moves. So if you look here, it means it goes upwards. I want this mass to move along here, this X component, because that's just what I want. So what I actually need to do is I need to flip that, I need to flip the prismatic motion on its head. So what I mean is I need to flip the axes. So I'm going to just delete that, I'm going to go rigid transform, and I'm going to bring that in and flip that round. Again, this is just because I want the axes to sit on the Z component. So basically the mass moves with that cable. So if I then bring that in, I'm going to drop in my rotational behaviors, go to standard axes, go to Y component axes, and I'm going to go negative and 90 degrees. You'll see why, because all I'm doing is I'm trying to get it to move on the X component. So I've actually knocked it on its head to make sure Z moves in that direction. From here, there may be one last thing that I've not done. Oh. So from here, let me just bring, can I move that? You can let me, there you go. I'm going to connect these up, and then if I come back, update model, you go, not exactly where I was going for, just saying, not at all. It's moving in that Z component, so if I go to prismatic joint, that Z component is there. It's moving in that right position. The biggest mistake I've made is I didn't flip the Y-axis back. So what it's done is it's just flipped it that 90 degrees and it thinks the rest of it's fine. So what it means is all I've forgotten to do is I've forgotten to flip it back. So if I just copy that and put that there and simply make that a a positive. When it comes in, it sets that prismatic motion to where I want it to be. And then what it'll do is it flips that prismatic motion, so it moves along that Y component like I want it. Then it flips it back. So then if I come back to my original design and click update, it moves to there. So I can now move to a testing. And I do quite like this. So if I run it, you get nothing. It's purely because if you think that I've not applied any real motion to it, gravity is moving in Z. I mean, we could see, because obviously this is a non-restricted coefficient of friction round the joint itself. So we could just simply shift, just for shits and giggles, we could just simply shift that Z component of gravity into Y, and let's see what let's see what gravity has an effect on it. So if I then run it again, not much, in short. Again, it's just because the joint's holding it in position. That's all it is. And if I do want to control this, which I do want to control this, I just want to look at what it can do. If I simply go to my joint, and then there's many ways I could do it. I mean, I could either do it that way. I could even as a student showed me the other day, well, I should say pointed out to me, you don't have to do it that way. You can. There's many ways you could do it, but just for something a little bit different, let's go to external torques and forces. Let's spin that in, tab that into there, and then let's go a torque around Z, click apply, and then do Simulink to PS converter. And let's just do a constant value. So if I run, the trouble is now I'm just running 1 Newton meter of force straight into it. So God knows what it'll do. Yeah, not be happy with me, in short. Yeah, see there where it's just pulled it straight up. So if I just go a little bit less, because it is only little, so it's not going to be far really. What I'll perhaps do is apply a motor to it. So I'm going to go actuation, bring in some motion, go by input. I'm going to make that an automatically computed, because what I'm going to do is provide the motion in there. And this is where I can actually have a bit more input to it. So if I go Simulink to PS converter, we've done this quite a few times, but Simulink to PS converter, I'm going to tell the system I want it to be behaving like a motor. Now, as we know, with a motor, I'm probably going to feed it in degrees. I can control the position. I could do radians, could do an output. I'm just going to go degrees. Then from there, I want to say that the actual filter process, don't forget, because I'm in motion, I'm going to need position, velocity, acceleration. That instantly tells me it's going to be a second order behavior, because I've got the 3 key elements that's coming out of it. So if I go filter, input derivative calculated, not a first order filter, but a second order filter, then apply, bring that in, and then what I'll do is I'm going to simply build a signal. So I'm going to go signal, signal builder. And this is where I can experiment a bit. So given the actual speed of how quick that responded, let's go set that to 0, and I'm going to set that to 10. And now this gives me a bit of a solid state that I can, oh, swine. From that position, push that up. Well, we'll run it at 1 degree, so this will go from 0 degrees to 1 degree, hold that present to 1 degree, and then bring it back over 10 seconds. Probably won't give us too much, but we'll see. So if I run that, yeah, if you wanted any more with it, we want to just take that up by a factor of 10 really. So with that, if I just make that in itself, I make that 10. Then when you run it like that, you get a bit more. And it will write it up, write it down. Now what's important with this is many things. We can actually look at the feed rates coming out of it. We can look at the torque that's needing to be applied to make this thing move. So if I go on to actuator torque, then apply onto there. I'm gonna do my normal, my PS to Simulink converter. So I'll go PS to Simulink converter. I'm going to duplicate that a few times because I want to use it a few times up here as well. If I come to there, and then if I come up to here, this is just oh, it's awful as far as messy. But with this now, if I then go on to scope, I go into here and then I'll do 3 inputs. I'll do scope. I just need to set my settings to a layout of 3 and apply. And now what I can do is snap into the feed rates of the actual cables. I can look at the torque that's coming out of that, and if I run it again, I knew the second feed rate wouldn't be much. And as you can imagine, all this is actually doing now is recording the amount of spool that's been released over that particular time. But what this allows you to do is to design your cables to actually make sure that you're going to fit the right distance that you need it to be. And it allows you to be more specific. This feed rate is only just such all over the place. Well, it's only so tiny just because of... Oh, excuse me. Goodness. Just because of the angles of it. So if you look here, the spool angle of it is basically very tiny, and that's why it's just noise in essence. But what's important with it is I can also look at the torque that's needed to make this thing move. Now if you look, any type of torque, when it outputs any type of torque, you'll end up with a spike. This spike is in essence the momentum to cause motion within them to that direction. Now because we've got gravity acting straight downwards, that tells us, we could presume that to be Newton meters, but it'd be nice if it was actually set to Newton meters. So let's just make sure that's coming out as Newton meters. So if I bring it out as Newton meters, it gives us a true representation of what's going on. I'll drop that second point out, drop you out as well. So I run it. So again, bring that in. So -4, so God, it's less than 9. It's like 0.2 Newton millimeters. So to actually cause this thing to move, to actually lift it at the speeds that we're running at, we'd need something that was going to be able to give us 0.2 Newton millimeters, but that's its maximum output. So I would always try and jump that little bit more, go to something like even a factor of 10 to put it into a safe position. So if I was to select a motor to actually operate these, because let's face it, these are little components, I'd be looking at 2 Newton millimeter output. That would be the minimum operation of a motor that I'd be looking for. Now the motor that's moved there, the way that it moves, you can presume, I don't need you to put this into your assignment, but for those of you who have got experience with motors, you can presume that that level of precision can only be operated within two types of motors. One would be stepper motor, or the other would be a servo. These are quite good selections for precision motion. DC motors, powerful, but bloody hell, they're like a wild stallion. Actually trying to control them accurately is very tricky. So you can presume that that would round down again the type of motor that you'd be after. Pulling that off the shelf, proving that with there, and then, I mean, I am not gonna insult your intelligence by going through the hand calculations of a pulley, just because it's a single pulley. But what I wanted to really show you with this is the basics of setting it up. This is the basics of running it, and if you want to add further pulleys to this, you actually can just bolt further things as you go along. Now there is lots and lots of examples built into MATLAB of these, but they're very, very elaborate. You've got millions of pulleys pulling everywhere, and it's incredibly confusing. I must admit, the one thing I didn't find in MATLAB was a single pulley explaining the dynamics and how these things behave and how you get them to move like you want them to. I'm just going to stop recording on that because that's all I wanted to do on the pulley, but it was just to give you an insight to them. Like I said at the start of this, what I wanted to do is set up small bite-sized bits of extra things that can be bolted to this. So I know one of you were interested in contact mechanics, more of contact forces. There is a custom toolbox you can download and install called Contact Forces. What I was going to do is go through that, show some of you how to use that, because I have used it. I used it on my PhD, and it is a great tool. But it is not something that is that comes with MATLAB itself. It's just something that you've got to get from File Exchange, MATLAB File Exchange. But it is a really good tool, really good set of tools. So I was going to go through that as well, but I'm just going to stop recording because I think that's all I wanted to show you on that.